its expectation. Through optimize this part, we finally get our Hamilton expectation minimized, and in this paper, it's with the matrix of the residue and the confusion matrix. So you can see actually the classical part of here is actually not written here, but it's the gradient search method, minimizing the Hamilton. And but the quantum computation part is the wave function and combined with those fast gates. So the result can be seen here. These two, on the right is the original label, and here in the middle are our prediction, and the leftmost are the residue. The upper part is actually the 5-circuit small circuit, and the 15th large circuit is here. We can also see the final confusion matrix with regards to here is the 8 features. So basically, they are of good performance as the true positive and the false negatives are quite good. But the differently the 5 qubit composed is a little bit better than the 15th one. But if we see the one onto the time domain, we can actually see now the 15th seems also to be quite good after some points over 150 times, while the small circuit they converge slower. However, we can see the accuracy actually still holds better with the small one, but the time efficiency seems to prefer the large qubit system. And we also try to analyze the KL callback convergence and the EV of these two results. So by eye, it is hard to tell the difference between the convergence of callback given by small circuit and the large circuit. But actually, with the F1 way test, we can see here indeed they are not with significant difference. And The fidelity also holds quite similar here. Both close to 0 shows the bias are strong as being labeled in only one of the binary class instead of evenly distributed possibility on either 0 or 1 label. And the CV of the fidelity gives the prediction by small circuit is more stable than the large one here, as you can see. And also there is a strange phenomenon that the CV are mainly goes upper than 0 for the large circuit, while for the small one it keeps oscillating around 0 both positively and negatively. And then we also choose one batch of 200 time samples to conduct the fit with the Rabi experiment and the pi-pulse fit, Ramsey fit here. So that's mainly the result I want to introduce here. And then finally, let me introduce myself a little bit. I received a master's degree in data engineering and machine learning with physics minor. During the bachelor, my degree is the math bachelor, and with the English minor. My work are mainly about dynamics neural networks in the lab, and using statistics, data mining basics skills. And in master program, in addition to the neuroscience research, I also goes into further with neuroimaging, neurocomputation, classification, detection, pattern detection, and with some cross fields in physics as well. And I'm very interested in mathematics and programming, also as some other nature science and technology. And due to the past background, I have done quite many projects still in machine learning related field. Of course, combined with biomedical and neuroscience. Like the EEG are the most familiar work with me. And the frequency spectrums and Bayes models combining stochastic process computational model with Python and MATLAB, C and C++, and also a little bit C# is my interest as well. So here are the two supervisors of mine. They're both working in the dynamic neural lab. The one is actually graduated from Nagoya University, and the one is from the University of Chinese Academy of Science. They are both very outstanding and inspiring to my work, and also with patience supervising me. So actually there are also more results in the appendix in my article. You can find it also with the code in MATLAB and Python on the GitHub. Thank you for today's listen.